Okay, so we have the equations that tell us, based on what the force is, what torque we need to apply in order to overcome that force and overcome friction in order to drive the screw upwards. That's only due to the friction that's occurring at this interface between the female thread and the male thread. Something that we didn't consider yet is think about how this clamp works. When I rotate this, you might not be able to see it, but I'll try to turn this towards you. This thing up top is not rotating, right? This little shoe up here, this foot is not rotating. So there is some sliding going on between the top of this thread here and this foot. So that needs to be taken into account as well, and that pops up in a lot of places, whether it is a clamp like this or some other lead screw application. For instance, I'm going to show another kind of lead screw. This was an example that I showed in class, where we have something that we're going to use like as a jack stand in order to raise a car, something like that. We've got some sort of base with a hole in it. It's kind of a conical base. And actually, let's flatten the top of this. I'm going to put a nut on top. And I'm going to put a screw through the nut. And I've got some sort of mass that I'm trying to lift up here. So here's a nut. Here's the screw. And the base, all that's doing is supporting the nut here. So the same equations that we have for turning the screw and leaving the nut fixed, they work just as well as if the screw is fixed against rotation and we rotate the nut. So imagine that this screw is fixed against rotation, but it's still free to translate up and down. And we're going to rotate the nut in this case. I'm going to pull on that nut, or I'm going to rotate it, and that's going to drive the screw up. If I'm lifting the load, raising it, then I'm going to get this equation. That's going to be the torque that's required to turn the nut. If I'm trying to lower the mass, then this is the torque that I need to apply to the nut in order to do that. But you can see in this case, we also have another instance where, in addition to friction at this interface here, between the thread and the female thread, we've also got some friction because we're rotating the nut relative to the base here. And that's pretty easy to model. It's a lot easier than the screw. So let's do that really quickly. The torque due to, we call it the collar torque. The torque at the collar. It's because there's some friction force that's acting at this mean radius, at the middle here. We've got actually a pressure that's acting over the bottom edge of the nut. So take that force, and we're going to multiply it by friction coefficient. And that's acting at a certain radius, kind of half way here. I can call this radius r of the collar, the effective radius of the collar. So this torque is just mu times whatever, well, the force that it has to resist is just F, whatever force that I'm applying down, or the weight of the mass, etc. Mu F times the radius of the collar. The radius of the collar is sometimes put in terms of a diameter. The radius of the collar is diameter over 2. So let's change this to dc over 2. And so that becomes pretty simple to model. The only thing that you need to keep in mind is that this is actually a pressure. It's acting over some area. So sometimes determining what effective diameter of the collar to use, it's probably not the outer diameter of the nut in this case or the inner diameter of the nut. We're going to put it halfway in between, kind of like we did a mean diameter for the screw. We kind of have a mean collar diameter that we're going to be interested in. In the case of this here, I'm not really sure. I can't chop this open in order to get inside there, but we would need to find out some sort of effective diameter where that friction is working. But this has to be taken into account whenever we're trying to calculate the total torque that's required to raise or lower a load. We're typically going to have some sort of collar torque that's also acting.